Now that we have done the moment curvature for 4 different cases, let us see how they compare with each other. In this one, again we are plotting moment in the x-axis, right, and we have curvature in the y-axis, and we are comparing two things. One is this AP equal to 600 mm square, which is a pure pre-stressed concrete section, and this is your pure RC, right. So if you see here, in a pre-stressed section you have initial curvature that we have discussed. Because we apply pre-stressing, the member tries to member up, right. So because of that you will have initial curvature, right, and these are equivalent systems that we have, as we've explained. So basically AS times Fy will be equal to AP times Fpy. So we have taken that tension forces of both the steel at yielding will be same, right, they are equivalent systems. So what we find here is, for due to the virtue of pre-stressing, I get higher cracking, and we have seen that we get cracking moment of 375.8 kilonewton meter, and you get cracking moment of 84.4 only for reinforced concrete section. That means my cracking moment is going to be much lesser for a reinforced section compared to that of a pre-stressed section. But if you look at the yielding, they give same moment resistance, and if you look at ultimate, again they give nearly the same capacity. But one thing that we can see is, if I take at one curvature, for example, let's say I take at 1, right. So if you plot here, this is the moment that I am getting from RC, and for the same thing, if I extend this, I get a moment of this from pre-stress. So what does it tell? For a particular curvature, the moment resistance from a pre-stress section is much higher than that of your reinforced concrete section, and we know that M by phi is your stiffness, which is your EI, flexural rigidity. So that means flexural rigidity for a pre-stressed section is going to be much higher, and the serviceability performance is going to be much better, right. So that is one thing that we have seen. Now if you talk in other words, from service moment point of view, you find that if I take one moment, let's say here, right, this is the curvature that I get for pre-stress, phi pre-stress, and this is the curvature I get for PRC. That means at a particular moment, my curvature in a reinforced concrete section is going to be much higher. Again, from serviceability point of view, it is not going to be good for a reinforced concrete, but pre-stressed section is going to perform much better, right. So that's what we are saying. Cracking load of a pre-stressed section is significantly higher compared to that of an equivalent RC section. And this is a, the previous one showed a close-up view, and now we have zoomed out and we are looking at how all the sections will look like. If you see here, again, the yield, ultimate capacities and ductility also nearly same. So ductility is this curvature ductility. We talked about Pu is going to be Pu minus Py by Py, and they are nearly same, right. So yield, curvature at yield is same, curvature at ultimate is nearly same. So the curvature ductility index is also, maybe I should say, mu phi, curvature ductility, right, they are same. Right. Next, now if we compare pre-stressed section, again this is pure pre-stressed concrete. Now pre-stressed concrete plus some compression steel, right, and you will find that adding compression steel is not really helping much. The cracking moment does not change, and yielding probably slightly it improved, but it is not really doing much, right? So if you see here, the ultimate moment resistance with compression steel, it went from 593 to 626, very marginal improvement in moment capacity, and the curvature also increased to 26 roughly. For reinforced concrete you had 23. So again you had marginal improvement in curvature at failure. The moment capacity also increased only marginally. So in fact, adding compression steel will help in improving the curvature at failure. However, because this particular section had very low reinforcement ratio, it failed in tension. That means the tension pre-stressing steel ruptured, right? So when the tension side is weak, by adding compression steel, we are not going to get much. That is the reason here also we were not getting higher improvement in curvature at ultimate. So no significant improvement in compression in ultimate capacity as well as ductility due to addition of compression steel. Right. The failure of a pre-stressed section with compression reinforcement occurred because of the rebar rupture before concrete reached a failure strain of 0.0035. Now if we compare pure pre-stressed, again pure pre-stressed without any non-pre-stressed steel. Now I have pre-stressed steel plus AST plus AC. This I am strengthening further with on the tension side as well as on the compression side. This you will find that because we did not change the pre-stressing, cracking did not really change, right? However, the yielding increased, the ultimate also increased, but the curvature ductility did not really change. So if I want both improvement in cracking yielding capacity and ultimate capacity, I can add steel on the tension side and compression side, and I can get both not reduction in ductility, at the same time increase in your capacity. So ultimate capacity increased, however the ductility remained nearly same with the addition of both steel, right? If we add more compression steel, then the ductility will increase, because now I have taken only 1200 mm square on both sides, equal amount of tension compression I am adding. That is the reason the ductility did not really change much. However, my yield moment and ultimate moment increased significantly. So this is the comparison. So you now you got an idea that for a section that is heavily under reinforced, putting more steel on the tension side is going to help me in improving the performance significantly. But for the section that is already weak in tension, by providing compression steel, I am not going to gain much in strength, but it will help me in ductility improvement, right? Now let us see, we have done it for a parabolic stress strain curve for a rectangular section. Now you may have T sections, you may have L sections, or you may have an arbitrary cross section can also be possible. So for such kind of sections, how do we do moment curvature analysis? So we have an approach called layer by layer approach. What we do is we divide the cross section like this. For example, an I section, we divide them into number of layers, and we know the thickness of the layers. So we know the centroid of each layer. For example, you see here, and then for any strain distribution that we assume, like what we have done, then once epsilon c is fixed, once x is fixed, right? Once x is fixed, then again at each of the centroid of this layer, using similar triangle, I can calculate the strain distributions in each layer. Now only thing is, if let's say if you're using a special concrete or different cross sections, then deriving this alpha or beta becomes more cumbersome, right? So rather we can do this kind of a layer by layer approach that will be applicable for any constitutive relationship, because what we are doing is, for any given strain, now that I have divided into small layers, I can quickly calculate what would be the compression force in each layer. Then when I integrate the force from all the layers, I get my entire compression. So, this is the very elegant way of doing for complex cross sections and for sections which are subjected with high strength concrete or high performance concrete or fiber reinforced concrete. For any type of concrete, if you know the constitutive equation, this approach is more generalized for calculating the moment curvature response. So, you get this actual stress distribution. So, you can get this kind of actual distribution. Now, with this layer by layer approach, we get this kind of idealized distribution. So, the force can directly be calculated because I know the strain in each layer. From the strain, I can get my stress. Stress multiplied by the area of the layer will give me the force. So, you can get this. So, this is the example, right. We have assumed some neutral axis depth x, and I assume some strain at the top. So, at any layer epsilon I can quickly calculate this using your similar triangle. Again, this is from similar triangle, right. So, epsilon I can be calculated from this, right, from at a distance of x, I have epsilon c top at this distance, which is x minus yi, okay. What is that? So, this is a similar triangle. Then once I know my strain, for this I know the relationship between stress and strain, I can get my stress in each layer as this. Then force in each layer is stress multiplied by the area of the layer, because I know the thickness of the layer, how finely I have discretized the section. I know what is the thickness is under my control, whether I divide them into 100 sections or 10 sections, so I know the thickness. So, I can get my area and I can multiply by the stress to get my forces. So, you add all of them to get your total compressive force. Then tension force again is the same way, using similar triangle, and again epsilon p, delta epsilon p, you know that. So, I should say this as, okay, this should be epsilon pi, right. This is your delta epsilon, okay. And sigma p is your E into epsilon p in the elastic regime, or follow the constitutive law, whatever that is assumed, and you get your total tensile force, right. So, this is a quick example. This is the way, it is a layer by layer approach, is a very generic approach to get your moment curvature response. Now, let us quickly do the same cross section that we have been using, 1 meter depth high section with a web thickness of 150 and flange thickness of 200, flange width of 500 millimeter. And it is having pre-stressing steel layer of 1196 millimeter square, and it has a compressive strength of 60 megapascal. Now, when you have 60 megapascal, you cannot really use parabolic model strictly, right. You have to use Thorenfeld's model, right. So, we are going to use Thorenfeld's model for concrete in compression, and I am going to assume linear behavior in tension until cracking. Concrete, we are saying that it will also contribute in tension up to a certain value, after that it will crack, right. So, and modulus of rupture is, or tension strength is 4.8 megapascal, and after that we are going to ignore the concrete, right. And ultimate strength is 1860, and initial strain epsilon pi is already given as epsilon pi is 0.0065, and we are going to use idealized bilinear model from IRC 112 and with the yield stress of 1618. So, same like what we have done. Now, this is your concrete model, Thorenfeld's model for high strength concrete, and for any given strain, this is the relationship I need to find out what is N and K, and similarly epsilon prime C also. N is given by this equation, F prime C is given to you, and K is 1 up to F prime C, or epsilon C is less than epsilon prime C, and K will be higher than 1 for any strain greater than epsilon prime C. So, when you substitute all these values, EC is working out to be 31,440 megapascal, and N, again using this equation I get a value of 4.01, and epsilon prime C is not constant 0.002, because we have seen that higher the strength of concrete, higher will be your epsilon prime C. So, that is why it has become 0.00279, again from experimentally calibrated equation proposed by Thorenfeld, I can get this epsilon prime C, and then K value I can get 1.55, and so in this way we can get all the parameters and go through the same process using your layer by layer approach that what we have explained, and you get different values of your moment and curvature like this, right. Okay. Now, again here ultimate is happening at 0.00276 for this cross section, again because it is not able to reach 0.0035 because the provided amount of reinforcement is less. Initial curvature and moment at 0 are calculated like what we have discussed before. Fine layers will give you more accurate results, but however computationally it will become expensive, so must be used in conjunction with a program, a MATLAB program or an Excel sheet, spreadsheet also can be used. So, this is the way we get your moment curvature behavior using your layer by layer approach. Now, let us look at how do we do the one sample calculation for strain of 0.00276, which is an ultimate condition here, okay, ultimate. Let us look at now how do we get this point, particular point, right. Okay. So, we are assuming 0.00276 and now we have already done the iteration. So, we know at what x it is going to satisfy equilibrium. So, that is equal to 135.61 millimeter, and I am dividing them each layer by 50 millimeter, right. I have 1 meter. So, you can see the number of layers, 20 layers are there, right. And for one layer, if you look at the L1, the top layer, the centroid is going to be at a distance of 25 millimeter from the top. So, the strain epsilon 1 in the first layer is going to be using similar triangle, you get a value of 0.00225. And now, I got the strain, now the stress I get it from your, again this is from your Thorenfels model, okay. So, you plug in all the values that you found previously and you get your stress as 51.46 megapascal. Now, compression force C1 in each layer is stress multiplied by the thickness multiplied by the width. Now, width of this section is flange width, which is BF. So, you can see for the width will keep changing, right, whether the layer is in the web or in the flange, the width will change. So, you get for first layer compression forces 1286.5 kilonewton. The moment of this layer is again I take moment about wherever the reference axis that I take, that works out to be 142.31 kilonewton. Like that we need to do for all the layers, right. So, this first layer strain is this, the stress is this, the force is this. Like this you will have force in all the layers. Now, once you get all the layers, then you take moment about any point and then you get your moment resistance. Curvature still remains the same. The curvature is nothing but your rotation here. So, this is curvature is nothing but epsilon c by x. That's it. So, that remains still the same. The only thing is, instead of using Whitney stress block parameters, now we are dividing by each layer, and each layer force we are doing it, and we are taking moment of all the forces, right. Okay. Here also the failure of the section occurred due to the rupture of the rebar, and the strain in the pre-stressing stand exceeded the limiting strain before concrete can reach 0.003. Again, this section is not we need to have more steel on this section. This is not a good design, right. We need to put more steel. Okay. So, this way we can calculate for the entire moment curvature response. So, let us summarize. So, we have explained the concept of equivalent stress block approach for rectangular section, how to use them for calculating the moment curvature behavior, and we illustrated how to determine the moment curvature with one example, and we also looked at different combinations of reinforcement for the same cross section dimensions, how each one of them is actually influencing the behavior. Finally, we also had a layer by layer approach for flange sections, and we use a Thorenfels model and calculated one point to get your moment and curvature for one layer. So, you can easily program it to get the moment curvature response for any cross sectional shape, and that can be used for any constitutive model for concrete or steel, right. So, with that thank you very much. So, we will continue the flexure chapter in the next session. Thank you.